Alright, so today we're going to finish off the linear programming unit, and then at this point you will have enough to make, hopefully, good choices about what topics you want to pursue. I'm not going to go through all the details because, one, you don't want to see algebra done in public. Two, the details are written up, hopefully cleanly, both in my notes and in the book. I want to try to emphasize the key ideas. So we talked last time about the simplex method, and instead of looking at solutions, what kind of solutions did we look at? Basic feasible. So the first lemma we need, there exists a solution, implies there exists a feasible solution. I'm being a little vague here. It should be if there exists a feasible solution, I'm sorry, this is basic feasible. And then it'll be feasible, optimal. So there exists solution, either feasible or optimal. I'm only going to do the proof that the existence of a feasible solution implies the existence of a basic feasible. The proof of the existence of an optimal implies the existence of a basic optimal is similar. So why do we care about this? This allows us to narrow down the search space. So rather than looking at all possible solutions, we just have to look at solutions whose non-zero entries correspond to linearly independent columns. And it's going to in fact tell you that there will be a limit to how many entries can be non-zero. Now again, this is still too large of a space to attack by brute force, but at least it's significantly smaller, it's got a very nice description, and then hopefully we'll find a good way to move through the space. So imagine ax equals b, and the components of x are greater than or equal to 0. We want to go from this to the fact that there's a basic feasible solution. So what's the only difficulty? What's the only thing that could cause us a problem? Why might we not be done at this point? So I say there's an x that solves this. Why might we not be done?
Is it 0? Is it
What do we need to be basic feasible?
to be linearly independent?
The columns of A corresponding to the non-zero entries have to be linearly independent. Maybe we have too many columns of A in play. So for instance, if A has m rows and n columns, then the small of m and n is going to be the maximum number of independent columns we can take. And so if x has too many non-zero entries, this will not be a basic feasible solution. It can't be. But maybe it's worse than that. Maybe we just happen to have columns that are linearly dependent. So the idea is we want to somehow swap out some columns. And if there's linear dependencies, we should be able to replace some columns with other columns. We're going to use a lot of very key ideas, very central ideas in mathematics to handle a problem like this. So the first is assume x is minimal. So again, what do I mean by minimal? Different problems have a different notion of minimality. If you've seen proofs of Fermat's last theorem in special cases, you're trying to solve, say, x to the fourth plus y to the fourth equals z to the fourth, or x cubed plus y cubed equals z cubed. You have Fermat's method of descent. You start with a solution, and you assume that the numbers are as small as possible. Maybe the largest number is as small as possible, maybe the smallest number is as small as possible, maybe you're doing square root of 2 is not rational, so you assume root 2 equals a over b, where a and b are integers relatively prime. And then you somehow show that there's another solution that's even more minimal, and that violates this assumption.
X here is one specific solution.
X is one specific solution. So if you want, I can call it x naught. So we need to assume x is minimal. So minimal in what sense? What's a good notion of minimal here? Any thoughts? So what's our difficulty? What's preventing this potentially from being basic feasible?
If you have enough non-zero entries such that there's too many columns.
Okay, so the difficulty is if I have too many columns in play, or if I have columns that are linearly dependent. So what's a good thing to sort the x by? The number of zeros, or correspondingly the number of non-zeros. Either one is fine, they're equivalent.
Yeah.
So let's choose an x that has the fewest number of non-zero entries. So fewest non-zero entries. And then the idea is we choose something with the fewest non-zero entries if we find something that has even fewer non-zero entries that violates the minimality here. So I'm assuming not only that x is greater than 0, I'll assume x is not basic. Because of course if x is basic, we're done. So all of this is conditional on the assumption that x is not basic. We'll get a contradiction. What is the contradiction to? It's a contradiction that x is basic. Okay, so how can we now continue? Well, since not basic, the corresponding columns are linearly dependent. So without loss of generality, let's let x be x1, x2, xl. Let's just assume that the non-zero entries are the first few. It doesn't really matter. Just notationally, this prevents me from doing indices on indices. If you know tech, it's not a big deal, but I know some of you are using Microsoft Word, and so if you ever have to write this up, I will spare you the horror, and I will spare myself the horror of seeing Microsoft do indices on indices. Alright, so this means when I look at ax equals b, I get x1, the first column of a, plus x2, the second column of a, plus, I'm sorry, not x's, I can't use c, I'll do alpha 1, x a1 plus alpha 2, a2 plus dot 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 plus alpha n, I'm sorry, alpha l, al equals 0 by linear dependence. Because the columns, the corresponding columns of A are linearly dependent, I have some numbers I can use. I can't use the x's because it's ax equals b. I can't use c because even though I'm not talking about it in canonical linear programming, we always try to minimize or maximize c transpose x. So I'll just use the alphas. So I have some linear combination like this.
Where not all the alphas are 0.
Where not all the alphas are 0. And in fact, how many of the alphas at a minimum must be non-zero? At a minimum, how many alphas must be non-zero? If they were all 0, then maybe they'd be linear dependent. So what do you know?
So 1.
At least 1. But what if only one of them is non-zero? Then you get a column of A is identically 0. Alright, well if a column of A is identically 0, it has no role in the game. Right? So, if it's identically 0, then I never see anything corresponding to its variable, so I might as well assume all the columns of A are non-zero. Not a big assumption. We also know x1, a1 plus dot 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 xl, al equals b. So if I subtract, and in fact I can even multiply this equation by any lambda, or maybe I'll do t for time, I would get x1 minus alpha 1t a1 plus dot 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 plus xl minus alpha lt al equals b. And we're almost done now. So we know at least one of the entries is non-zero. Let's assume it's alpha 1. Okay? So we assume alpha 1 is not 0. And because alpha 1 is not 0, if I take t to be 0, I just return and get back the original solution I started with. Think of t as a dial now. I'm going to turn up time. Okay? If I have to go backwards, I would turn back time. If I want to go, depending on the sign of alpha. Okay, I was seeing if anybody would get the reference. Alright, so nobody got my references to pop culture last class. So now here, why do I want to adjust time? What am I going to do if I adjust time? What can I do? I'm sorry?
That made a noise.
Yeah,
No, it's
that's my
Okay,
computer.
good.
Yep. So what will I be able to do by adjusting time? Let's assume without loss of generality alpha 1 is positive. So assume alpha 1 is greater than 0. I want to increase time a certain amount. What can I do if I increase time?
Scale out.
What's going to happen as I increase time? When t equals 0, I just have my original solution vector. As I increase time, is these new coordinates the solution, a new solution? The only thing I have to worry about is, are all of these coordinates non-zero? Well, since they are all non-zero at t equals 0, they will still be non-zero for small values of t. I keep increasing time. What's going to happen as time increases?
x1 equals alpha 1 t.
I'm sorry?
x1 eventually equals.
At one point, this will be equal to 0. At which point I've now dropped a column, and I now have a solution with one fewer column. Now the problem is, I may not be able to let t get that large. Because maybe as t is getting that large, maybe one of these earlier ones becomes negative. Well, that's fine. All I need is that as I increase time, eventually one of these components becomes 0. Or maybe several become 0 simultaneously. That's fine. By continuity, they can't go from positive to negative without going through 0. So as you increase time, there will be some critical value where at least one of these becomes 0 and all the other ones are still going to be positive. And what you now have is you have a new solution with fewer coordinates. So, unfortunately, we've run out of backward space, but so I was right here. As increased time t, eventually at least one coefficient below is 0, rest are still greater than or equal to 0, have a new feasible solution with fewer non-zero entries. And that's a contradiction. And so that's the proof that if you have a solution, you have a basic feasible solution. So this is a really beautiful idea. This is used again when we look at optimal solutions. This is used again in the simplex method. The idea is you start with something that's good, you have some notion of minimality, and then you look at the tweaks, you look at the adjustments. I start throwing away some things, I start shuffling things around, and I continue this process until one of my coefficients hits the critical threshold and becomes 0. Okay. Any questions on how a feasible solution implies the existence of basic feasible? Okay. I'm not going to do the same game for optimal implies the existence of basic optimal. So what I want to do now is I want to go back to the simplex method. Bless you. I will prove phase 1 in full detail because the proof of phase 1 is much easier than the proof of phase 2 and much less algebra, and so I will concentrate on that. A key step in the proof of phase 2 is what we just did here. So remember, there's two phases. Phase 1, find basic feasible or show none exist. And then phase 2, given basic feasible, find basic optimal, or show none exist by driving cost to minus infinity. So not only will it show us that there is no basic optimal, it'll actually let the cost go all the way to minus infinity.
But then that basic feasible you're given wouldn't really be basic feasible.
No, it's still basic feasible.
But doesn't that imply...
Basic feasible just means it satisfies the constraints. It satisfies ax equals b, x is non-negative, the corresponding columns are linearly independent.
Yeah, the end of it.
So at this point, we can always talk about feasible solutions without looking at whether or not it does a good job. So now we want to try to find things that do a good job. So the way it's going to work is we're going to assume phase 2 and use phase 2 to do phase 1. And then we'll prove phase 2. Now at first this looks absurd because phase 2 requires the existence of a basic feasible, and we're going to use phase 2, which assumes the existence of a basic feasible, to prove phase 1, which is finding a basic feasible. The reason this is not quite a circular argument is because we're not applying phase 2 to the same problem. So we talked a little bit about this last time. If you run American Airlines, give me a schedule that satisfies all of your constraints.
No flights.
No flights. You run a movie theater. Give me a schedule that satisfies all your constraints.
Shut down.
Shut down. Okay? So there are solutions. Okay? These are not close to optimal solutions. Alright? Hopefully American Airlines makes more money by flying planes than having the planes grounded. Hopefully the movie theater makes more money by showing movies rather than having the theaters closed. But if we're just trying to find the existence of a basic feasible, frequently we can just look at it and see. So proof 2 implies 1. So we're given ax equals b, we want x greater than or equal to 0, and it's been so long. Are we trying to minimize C transpose x? Yes. Trying to minimize, or maximize, right? No, minimize.
Yeah.
We're trying to minimize C transpose x. Okay. Do I really care right now that we're trying to minimize or maximize C transpose x? No, we're just trying to find a basic feasible. This part is only, once we have our feasibles, trying to find which one we like the most. Alright, so how do we do this? So consider a tilde, which will be a, and I'm going to add I to it. And let's let x tilde be x, and then we'll add a vector z to it. And we'll still assume this is greater than or equal to 0. So I want to solve ax tilde equals b. A tilde. So I've expanded the matrix. So I've basically added an identity matrix that has the same number of rows and columns as entries of B. Okay? Can anybody give me a solution to a tilde x tilde equals B?
So it's a plus I?
No, it's just a, and I'm just appending an identity
appending
matrix
it.
to the right of it. So can you give me a solution, a choice of the vector x tilde z tilde? Or if not, if you notice there's a small technicality, what's the technicality that's preventing you from giving me a solution?
You add a bunch of zeros to your B, then you can do it.
Well, no, B has the right dimension as this. I need to tell you what x and z are that solve this. Can you give me a choice of x and z that solves this?
Oh.
Zero vectors
For which? So take...
for that. For x tilde. Because
Well, if you take the 0 vector, then you would get 0 equals b. So I can't just take the 0 vector. I want to solve ax tilde equals b.
Appended with the zeros?
So you want me to have z be zeros?
No.
So if z is 0, it reduces to the original problem. So what do you think I want to take to be the 0 vector? X. So if I take x to be 0, it reduces to trying to solve identity times z equals b. This is a prereq for this class. Try to solve identity z equals b. What should z equal?
B.
B. Hey, look, I found a solution. Now, this may not be a feasible solution. What could prevent this from being a feasible solution?
not be greater than 0.
B might not be greater than or equal to 0. So when we're doing our problem, if B has a component that's not greater than or equal to 0, well, I can just adjust the corresponding row of A by multiplying through by -1. I can assume B is greater than or equal to 0. And I can put it back in canonical form. So in fact, without loss of generality, I can assume B is greater than or equal to 0 as well. And now, this will give me a feasible solution. So we found a feasible solution. Phase 2 just says, given a basic feasible solution, find a basic optimal. Well, in fact, not only is this a feasible solution, it's a basic feasible solution. The columns are clearly linearly independent because they're just the identity matrix. So this is basic feasible. To the new problem. So it's not a feasible solution or a basic feasible solution to the original problem, but it is a feasible solution, a basic feasible solution to the new problem. Okay? Now the difficulty is I want to do phase 2 and somehow run phase 2 and get a basic feasible solution to the original problem. When I'm trying to do linear programming problems, I have my constraints, and I also have something I want to maximize or minimize. I need to put in that function. So now, let's add our objective function. I want to minimize the vector 1 transpose x tilde. I'm sorry, I want to minimize 0, 1 transpose x z. So it's just z1 plus zm. So again, I can choose any objective function I want. What I'm going to do is I'm going to say the cost of my solution is the sum of the z's. And I want to minimize the sum of the z's. So if I had to choose a vector z, I would start off with a 0 that's the same size as x, and then I would have a 1 that's the same size as z, or the same size as b. And this is the objective function to minimize. Well, phase 2 says that if you give me a basic feasible solution, I can find a basic optimal or prove that none exists. So let's look at the different possibilities. What's the possibilities? So run phase 2. So case 1, could the cost go all the way down to minus infinity? Do we have to worry about the cost going to minus infinity? No, why not?
Because it said it's greater than 0.
So b is greater than or equal to 0, so the coordinates z have to be greater than or equal to 0, right? We're looking for a solution where the inputs, x and z are non-negative. I'm never going to be in the case where the solution is going to be going to minus infinity. There will be two possibilities. It'll either terminate at a positive number or it'll terminate at 0. So case 1 terminates at a cost of 0. Well, let's think, what would it mean if it terminates at a cost of 0? If it terminates at a cost of 0, what's the sum of the z's? 0. So what does that mean each z must be? Each z must be 0. Well, if each z must be 0, and I have an optimal solution to the original problem, then the corresponding x must be a feasible solution to the original problem. So, have, let's call it x final and z final is going to just be all zeros, is the solution. And that implies xf is a feasible solution to the original problem. So this is That's wonderful. If the cost goes all the way down to 0, that means each of the z's must be 0. So whatever my optimal solution is, the x component of that must be a feasible solution to the original problem. So this is an auxiliary problem that's helping us along. Okay? And now that we have this, we now have a feasible solution to the original problem. We don't necessarily have a basic feasible, but we know how to convert from feasible to basic feasible, so this is not a big deal. So is everybody comfortable with what happens in the case when the cost goes down to 0? So what's the only case that's left?
You have a or you have a basic optimal.
Well, and what's true about that basic optimal?
Non-zero.
Cost is non-zero. So what would it mean if the cost is non-zero?
At least one z has to be.
At least one z
not
has to
zero.
be, right. And if there had been a basic feasible to the original problem, what would the cost have been? If you had a feasible solution to the original problem, what would you know?
You mean with a z, with a non-zero z?
Well, no, if I go back to the original problem, imagine I can solve this before I introduce any of the z's. So imagine there is a basic feasible solution or a feasible solution to this problem. When I then get to here, what would I be able to make my cost? So if I could solve the original problem, what should I take for z? I think I heard somebody starting to say it. 0. If I can solve the original problem, take z to be 0, and then when you plug that in, what will you get for your cost? 0. So if I tell you that the basic optimal solution to this new problem has a positive cost, there can't have been a feasible solution to the original problem, because that would have given a smaller cost.
So that's the only case.
So that's the only case. So case 1 was, let's say it terminates at a cost of 0. So case 2 terminates at a positive cost. Terminates at positive cost. What does this mean? If original problem had feasible solution, could have cost of 0 here, contradiction. Therefore, the original problem does not have a solution. Therefore, original has no feasible solution. And that's the proof of phase 1 of the simplex. Okay? So again, very clever idea here. Rather than studying the problem you were originally given, study a related helper problem that's easier to solve. And then once you solve that, use that to deduce things about the problem you care about. So lots of great stuff going on here. And again, it all comes down to, in some sense, the method of divine inspiration. Which is easier, integration or differentiation? Differentiation. As much as I want to, I cannot write down a derivative that my students cannot get. Oh, I'm sorry. I can write if they were really good. This is being recorded. If you really know your calculus well, I cannot stump you on a derivative. You can just keep applying the rules of differentiation and keep hacking away and get the solution. I can very easily write down integrals that people can't do. Sometimes people see a good way to do them. If you think you know how to do an integral, how can you tell if you're right? Take the derivative, right? So the method of divine inspiration is very easy to check. And for those of you who know about P versus NP, a lot of times there are some algorithms where it may take a long time to find the solution, but it's very quick to check and see if you have a solution. So for example, does anybody know the antiderivative of natural log of x? I'm sorry?
That's a good
Right. Anybody know?
X log x minus x.
Very good. X log x minus x. And if you start playing with, well, if I take x log x, if I take the derivative of this using the product rule, the derivative of x log x by the product rule, I get the derivative of x, which is 1 times natural log of x. Oh, that's good. Plus x times the derivative of 1 over x. So I'm off by an extra plus 1. So I need to subtract a function whose derivative is 1. So I can take my guess and I can refine my guess. With a little bit of work, maybe you could get x squared log x, or maybe x squared log cubed x. And you try to play these games and correct. Once you see how to start something like this, it's not so bad. If I give you, I don't know, natural log of sine of x plus x squared, and ask you, what's the antiderivative? You're up the creek. Or I could even give you something like e to the minus 1 over x squared, where there's no closed form of the antiderivative. Fortunately, for linear programming, we are in a situation where we can just look at a related problem and see the solution. Okay, so that's phase 1. Now we want to do phase 2. Given a basic feasible solution, find a basic optimal solution, or prove one doesn't exist. So I don't want to go through all the details of this. The details are in the book. I want to just give a quick sketch of what's going on. So we can assume a basic feasible solution exists. If it doesn't exist, well, phase 2 is pretty easy, right? Phase 2 says, given the existence of basic feasible. Okay, so we have a basic feasible. So we know there's at least one candidate for the optimal solution. And we have this lemma that we didn't discuss in great detail that says if there's an optimal solution, there's a basic optimal, so I only have to start checking. So now, let's imagine I have a feasible solution, basic feasible solution. So phase 2. So have a basic feasible solution x1. We have a way to tell if x1 is optimal. So this was the stuff you were supposed to read about looking at the dual problem. And we have this beautiful relationship between values of solutions to the original problem and values of solutions to the dual, and we can check and tell if something is optimal or not. If there's a gap, it's not optimal. It's wonderful that you can do this. One of the consequences of this is if you're trying to solve a scheduling problem, you can say, alright, I can tell I'm not at the optimal, but I can also say I'm off by at most 0.5% or 0.1%. I might be off by less, but I know I'm off by at most this much. And it's wonderful to be able to quantify how close you are. There's a couple of things in mathematics that are like this, where you have these kind of existence arguments. You have some idea of how far away you are. So let's say we have a basic feasible solution. Check and see if optimal via the dual problem. And if it's not optimal, what we're going to do is we're going to play the column exchange game. So the way you should be looking at it is one of the non-zero entries corresponds to a column that's too expensive. And you want to replace that with a cheaper choice. This is exactly the argument we did when we were looking at going from a feasible solution to a basic feasible solution. So, play similar game as did in feasible to basic feasible. Exchange expensive column for a cheaper one. And so I'm not going to go through all the details of the algebra, but you're going to have again the same notion of a time dial. So have time dial. And now you have two possibilities as you allow time to evolve. Either eventually one of the components becomes 0, in which case you have to stop, because if you go any further, you would have a negative entry, and you're not allowed to have negative entries. Or, you can let time go all the way off to infinity. And if you're going to go all the way off to infinity, your cost will go down to negative infinity. Because you keep making things cheaper. So, let time go. Either must stop at some time, say t2, or continue to infinity, sending cost to minus infinity. Okay. So if we come over here, then we're done. Right? If we end up in the case where the cost is going to minus infinity, we're done. We've shown that there is no basic optimal solution. So the only difficulty is if we end in this case. What do we do now if we end in this case? So we started with a basic feasible solution. We did this algorithm. We ended up with a new basic feasible solution that had a lower cost. Now what do?
We check if it's optimal.
I'm sorry?
We check if it's optimal.
We check and see if this is optimal. Lather, rinse, repeat. Shampoo mathematics. We just keep doing it again and again. What we do is now we take this and we feed back into here. And we see if it's optimal, we're done. If it's not optimal, we play the same game as before. We look at these linear combinations. We have a new time variable, except now instead of calling it t2, we call it t3, or we go off to minus infinity.
That doesn't seem like a very efficient way to do it.
So that's the real question, is how efficient is this?
Because you could do that.
Oh, yeah. Well, okay, so that's the question, is will we do this forever, or will eventually the algorithm terminate? So there's two possibilities. Either eventually I get to this subcase where my cost goes off to infinity, or I keep going into this subcase.
So that has to have a finite number of times that you do it.
Exactly.
But it could still be, like 1,000 times.
Oh, 1,000 times I'd be thrilled. I would be thrilled if it was as short as 1,000.
100,000.
I'd be thrilled. You got to give me hefty numbers. If you don't even like 10 to the 80th. Yeah. So the question is it possible that I could just cycle through here forever, or must I eventually terminate if I keep going into this case? So clearly, it's got to terminate at some point, or this would not be one of the greatest algorithms in the history of mankind.
Because you keep losing columns if they turn to 0.
But maybe a column comes back later. I mean, you might be able to prove that doesn't happen. How many basic feasible solutions are there?
That big number.
A big number, but finitely many. Only finitely many basic feasible. Therefore, it terminates.
So this algorithm won't keep checking once it's already checked somehow?
I'm not sure about that. I should know I don't. What I would hope is that maybe once you throw away a column as being too expensive, it's not going to come back.
Yeah.
But it doesn't matter. Even if it comes back, there's only finitely many columns to check. Or finitely many combinations of columns to check.
Yeah.
Now, that finitely many is too much to do by brute force. So the hope is that when it's doing this checking, it's checking in an efficient manner, so that it searches the space quickly.
And does it check if it already checked it and then won't check it again, maybe?
My feeling is I don't think you could ever have a repetition.
Okay.
Because, no, you can't, because if you checked the exact same combination of columns twice,
Yeah.
they would have
Then
the
the
same
rotation
cost.
would-
They would have the same cost. And every time you do this, the cost goes down.
Right, okay.
So because the cost goes down, you can't get to the same state twice. Now again, it may take an enormous amount of time to get there, but you will only do it finitely many times. So now I'm hoping to seeing why we care so much about basic feasible versus feasible. How many feasible solutions are there? Infinitely many. How many basic feasible solutions?
None.
Finite, not. Okay, less. Okay? There are only finitely many basic feasible. And so we can now go through the basic feasible. I am not describing at all why this runs quickly. Okay?
It might not.
I think it runs quickly either all the time or almost all the time. I'm not sure exactly how good the down-seek simplex algorithm is. But for the most part, it's going to run quickly.
So you're only checking for one basic feasible. Like once you hit one solution, that's a basic feasible solution. You're done.
Once you hit one optimal solution.
Right. Or yeah. Sorry. Once you
Right.
hit optimal.
Yes.
Okay.
Right. Because
that's different. Like because I was just thinking in terms of the homework problem. One of the homework problems we had to do where we had to calculate how long it would take to. That's like it's finitely many solutions.
how long to calculate what?
How many basic feasible solutions
Okay, yes,
there
right.
were.
Right, it's a huge number.
Yeah, which
Right.
is pointless. So
Right.
Something of all the
yeah, so it
Exactly.
so shooting from 1 to 1,000,
Yes.
which is just a lot.
Yeah, no, it's a nightmare. You would never want to do this. Okay. Any questions on why this works? So again, I'm skipping a couple of the algebraic details, but I hope you get a sense that it's the same game as what we did for basic, for feasible implies basic feasible. We do this kind of column exchange. We take something that's giving too much of a cost, and we replace it with something that's cheaper. For those of you who remember Calc 3 and optimization problems, or those of you who will be TAing the course and will have to remember this pretty quickly, when you look at the gradient vector tells you the direction of maximum change. And it tells you the direction to go. But it may not be the best way to go. Have we done, do you dogs know calculus in this class yet?
The locally optimal version.
Yes. Have we done that in this class? Okay. If everybody's fine with this, I want to show you a little bit of the difficulty of finding solutions. And maybe I'll talk about this instead of going into integer linear programming right now. So, whenever you get a math problem, the first thing you want to do is you want to solve it. After you solve it, then you can be greedy and want to solve it quickly. So here's a great series of problems. Do dogs know calculus? So the person who owns the dog, his name I think is Tim Pennings. He's from Michigan. His dog is named Elvis. And according to these experiments, the dog seems to know calculus. So I'm just going to talk about the more interesting one. So here's land. Here's his dog in the water. My artwork is terrible, so I will draw his dog as a point. And what Tim does is he throws a stick near the dog, and he sees the path the dog takes to get to the stick. If you've seen this before, please don't speak up right now. Alright, if the stick is here, what path will the dog take to get to the stick? Okay, straight line. What about if it's here? What if it's here? What if it's here?
Might go on the beach and run on the beach. It's faster to do that.
It might. Definitely by the time we get all the way down to over here, if the dog knows calculus, the dog knows take a path like this. And the dog's analysis of what angles to take is actually not so bad. And the reason is you run faster on land than you swim in water. And so if you're very close, for a problem like this, when it's this close, I would still guess here it's straight line. Just because if you swing this to see, the best you could do is running. But I mean, maybe it goes. Is this plus this shorter than something like that? What happens is the dog's speed on land goes to plus infinity. So imagine your dog runs at plus infinity on land.
It's straight.
Yeah, you go straight down, run, and then straight up. And so you can actually use this to prove the arithmetic mean, geometric mean inequality by imagining, an infinitely fast dog. What's nice is there's got to be some critical distance where the dog is indifferent between these two paths. And then if you move the stick just a little bit further, if this dog truly groks calculus, then all of a sudden you have a phase transition. You have a bifurcation, you have very different behavior. So there's a lot of wonderful mathematics in something like this, that a very small change in initial conditions leads to wildly different paths, going from a path like this to a path like this. And if you think about what's going on, what's the advantage of the straight line path?
Shortest distance.
It's the shortest physical distance.
Yeah.
It may not be the shortest time, but it's the shortest physical distance. There's another advantage. There's an easy way to describe the straight line path. At each moment in time, do what is locally best. What decreases your distance to the endpoint the most? So if I'm here, locally the best thing I can do to decrease my distance is to move straight towards the stick. This is the Stalin approach. Sometimes it is better to take one step backwards and then take 2 steps forward. Okay? Locally, do something suboptimal. Okay? Locally, go away from the locally optimal path. Because globally, it's better. And so the problem is you can get trapped in a local extremum and not find the global extremum if you do what's locally best. And that's one of the difficulties. So when you're doing the simplex method, one of the dangers is, will you converge to the correct solution? Well, fortunately, yes. Because as you keep doing it, if you're not optimal, you will keep going. The question is, how long will it take? Alright, so this was the first thing. The second one is, how many of you have seen the Euclidean algorithm? How many of you know how fast the Euclidean algorithm is? So, Professors Gowdy and Adams have many debates. One of them is on which is better, the trefoil knot or the Euclidean algorithm. In the interest of full disclosure, I have not seen the debate, but I do not need to see the debate. It is clear that it has to be the Euclidean algorithm. It has wonderful applications in cryptography. And so the point of the Euclidean algorithm is to find the GCD of numbers. So Euclidean algorithm. So the goal is find the GCD of 2 numbers x and y. And so we're going to go as follows. So start off y equals x plus, and so I'll assume x is less than y. If x happens to equal y, this would not be a hard problem. So what I'm going to do is I'm going to write y as some multiple of x plus a remainder. What can you tell me about the remainder? Less than x. And you can tell me a little bit more. I'm sorry?
It's greater than 0?
Greater than equals 0. It could be 0. Right? Could be 0. And so I basically subtract off as many copies of x as I can from y, and what's left over is my remainder. Now, I write x as a multiple of R1 plus a remainder. What can you tell me about the remainder R2? Less than R1. And I can keep going. I can write R1 as A3, R2 plus R3, 0 plus equal to R3 less than R2. And I can continue. Every time I do this, the remainder has to decrease by at least 1. So eventually I will go down and I will get a remainder of 0. So eventually I will get RL equals AL plus 2, RL minus 1 plus 0. Now the interesting thing is the greatest common divisor of x and y is the largest number that divides both of them. So imagine D is the GCD of x and y. Well, R1 is equal to y minus A1x. So the GCD of x and y is the same as the GCD divides R1. So let's say D is GCD of x and y. This means D divides x, D divides y, nothing larger than D divides both of them. Clearly, D divides R1, which is y minus A1x. So the greatest common divisor of R1 is at least D. The greatest common divisor, of R1 and x is at least D, because D divides both of them. Could the greatest common divisor of R1 and x be larger than D? Well, if it was larger than D, it would also divide y. Cannot have GCD of x and R1 greater than D. Therefore, the GCD of xy equals the GCD of R1x. So if I want to try to calculate the GCD of x and y, it's the same as the GCD of x and R1, which is the same as the GCD of R1 and R2, which is the same as the GCD of R2 and R3, which eventually is the same as RL minus 1. So I have a way to calculate GCDs. Okay? How long could this algorithm take to run? Worst case scenario, how many steps?
The max of x and y.
The max of x and y,
Or
so,
y.
so it would be, I'm sorry?
Why?
Not y.
Well, if x is 1, then... Oh, no. Actually,
So the worst case is if x is 1 less than y. You know, it's going to take basically x or x minus 1 steps. Worst case, x or x minus 1 steps. So I'm just trying to look at this and see how long things take. Every time I iterate this, I could be in a horrible situation where I only decrease by 1. And if that's the case, it could take me on the order of x steps to get all the way down to the final thing here. Okay? So if you look at the Euclidean algorithm like this, it works, it's easy to code, but it doesn't necessarily look efficient. It turns out the Euclidean algorithm is amazingly efficient. One of the most efficient algorithms known to man, woman, child, roadkill, whatever. This is the algorithm. Okay? It takes on the order of log x steps to run. So the result is every 2 iterations you decrease by a factor of 2 or more. So I'm going to just erase a bunch of things here. So every 2 iterations decrease by at least a factor of 2. And I can even put the exclamation point as either excitement or as a factorial. Both work. Okay? This is wonderful. So let's look at what goes by this. What I mean is, if I look at x and then I look at R2, R2 is at most x halves. Okay? So case 1, let's say R1 is less than or equal to x halves. Are we good? Yes. Life is good, as R2, which is less than R1, which is less than x halves. So if R1 is really small, then we're in great shape. So this is the idea, is in mathematics, split things into cases and use the givens of the different cases to attack the problem. So if R1 happens to be really small, we've moved a lot in our first step, and I don't really give a what happens in my second step. What's the other case? So R1 is greater than x halves. Well, if R1 is greater than x halves, what's going on here?
You don't know if R2 is going to be...
So again, maybe x is really close to y, maybe a is equal to 1, and maybe R1 is large. So R1 is large, but now I have to write x equals A2R1 plus R2. What must A2 equal? A2 must be 1. Why? Because if A2 was equal to 2, then the right-hand side would be larger than x. Right?
That has to be an integer.
Has to be an integer. So if A1 was 2, then this quantity here would exceed x.
Right.
So now I get x minus R1 equals R2. But what do you know about x minus R1?
Less than x halves.
So
Or close,
R1,
close to 0.
so R1 is greater than x halves.
Yeah.
So this has to be at most x over 2. So this is less than x over 2. And we win.
So it actually doesn't end up taking...
It doesn't end up taking order of x steps. Every 2 steps, you are guaranteed to decrease by at least a factor of 2. So then the question is, how many steps would you have to take? Worst case scenario. So every 2 steps is a factor of 2. So is everybody comfortable with this? Can I erase this? So, time cost. Every 2 steps is a factor of 2 or more savings. So, if I have n steps, I basically need 2 to the n halves to equal x. Right? So that means the log base 2 of x times 2 equals n. So that's the cost of the Euclidean algorithm. It's not an order x algorithm, it's an order log x. Another way to view this is it's polynomial in the number of digits of x. So the logarithm of a number basically is just counting how many digits your number has. So if you double the number of digits, the algorithm's runtime doubles. That's not a bad cost at all. You can use this with 100-digit numbers without any difficulty. 10,000-digit numbers, which we talked about, numbers, not a problem. So you just have to be a little careful as to how you store things. So a lot of times algorithms that don't look too efficient turn out to be very efficient. And so again, I'm not proving to you why the simplex algorithm runs as well as it does. This is a first course in the subject for most of you. I don't really want to go into that amount of technical detail. If you want to, as a project, to look and see, why does the simplex algorithm run this well? Are there cases where the simplex algorithm does not run as well as you would expect? By all means, I think that would be an absolutely outstanding project to do. Right now, we just know the simplex algorithm works. The universe might die a heat death, multiple times before it finishes. We don't know. But we know that it works. We know that it terminates. Okay, so I think this is a good place to stop for today, and I just want to touch base about various projects.